It's visible?
Yes, sir.
Yeah. Here we have to continue the next the topic, that is characteristic of light. We have to actually the intensity, the power per unit solid angle. That is, we have to that intensity is like brightness. The more focused one, that we have already discussed about the numerical aperture. Okay. Uh, Therefore, that we have to find out that the intensity is the brightness, and that is the numerical aperture at a particular point, concentration of that point that gathered of the light at a particular point, that we are calculating the numerical aperture. If the numerical aperture is good, then that will be the we have the good transmission of signal. If the numerical aperture is low, then that spreading of light at particular point that will be take place, and that is a dispersion in the signal that will be pointed out. Okay. Therefore, the intensity like brightness and is measured as the rate at which light energy is delivered to a unit surface area, or energy per unit time per unit area. That is, you are calculating the SI unit, or the luminous. The SI unit the light or intensity is the luminous, and intensity is the particular we have to calculate for that light. The When you are talking about the light, that having the lambda with the colors also, red spectrum, the color spectrum is available. Then the spectral width, the purity of color that we have to get with the help of del of lambda. And polarization, there are three types of polarization available. That is the yes, linear polarization, then circular polarization, and elliptical. The Here the behavior of light is explained using three different theories. First one is particle theory, wave theory, and quantum theory. So we have to concept of we have to get the behavior of the light, that will be explained with the help of this concept, that particle theory, wave theory, and quantum theory. The particle theory, principle of refraction and reflection, that will be how the two planes, and with the help of that, if our light pass through that particular plane, then that will reflected and reflected the light. That with the we can calculate the Snell's law. That is the particle theory we are getting for the principle of refraction and reflection. Then wave theory, principle of interference and diffraction, that can be find with the help of the wave theory. The wave theory, that concept, we have get the principle of interference and diffraction in the light. Then quantum theory, principle of dispersion, emission, and absorption. That will three part that will be discuss about the principles of dispersion, how the light is dispersion while passing through the core region. Emission of light, absorption of some light is absorbed due to the particular light pass through the core core that region. That time some light is absorbed, that will be the due to the atoms are available at the core. That is in SiO2. Therefore, that energy will be slightly less. Here the next the we have the this is a field uh, distribution in plane of electromagnetic wave. Here we are showing here the one minute, the the field distribution in plane E and M waves. Here we have the X, Y, Z three coordinate systems available. Okay, and this that will be perpendicular, mutually perpendicular to each other, X, Y, and Z. Okay, that 90 degree to each other, that having three axis, and that particular plane is divided into the three axis, X, Y, Z. Okay, and the here uh, the actually this electrical field, the this we are showing, and this is a magnetic field. We are perpendicular to each other. Okay, and this we are showing that this z-axis, that along the z-axis the light propagate through the z-axis. Means through means that to at the z-axis, from the just the axis follow the z-axis for the light travel along the z-axis. But in that light that having the electrical and magnetic fields are available, that fields are perpendicular to each other. Therefore, this E field that we are showing, that is the actually the parallel to the x-axis, and H field is parallel to the y-axis, and that follows the sine wave, just like a sine wave that having the fields that having the sinusoidal waveform that will be the we are getting here. Therefore, this E is perpendicular to H, means E is parallel to x-axis, H is parallel to the y-axis, and the propagation of light along the z-axis that indicated by K, that propagation constant is indicated by the K. Okay, therefore K is equal to 2 pi upon lambda. That is, a 2 pi is the one cycle, and divided by the lambda, the frequency, that is the wavelength of that particular signal, that is the light. Therefore, that can be getting that K is 2 pi lambda, and we can find out the K also. If you know the lambda value, then we can find out the K constant. Okay. Therefore, these are the field distribution in plane E and M waves, electrical waves and magnetic waves that are perpendicular to each other and travel along the these waves are travel along the z-axis. We are showing here the diagram for field distribution in plane E and H waves. Okay. Then next is here the elliptical polarized light. Here this is a just like how we are showing the three planes, the two planes having the electric field and magnetic field, and the waves will travel along the z-axis, and that will be a perpendicular to each other. Okay, that we are getting the how the field distribution in plane E and M waves that we are showing here. Okay, then the next one is the electrically polarized light. Here, same thing XYZ. We are showing the elliptically polarized light that we have the angle difference between the EX and EY waves, that plane that having the delta. That is the difference is available, and with the help of that difference, we are getting the here elliptically polarized light. Here we have the slightly difference that we have the delay in that two planes, EX and EY, that having the delta, and that will be delay in that is angle. That will we are getting the elliptically polarized light. Therefore, here we are getting here the how the that will elliptical form, that polarization we are getting here, this view, the spiral type that will be along the z-axis that goes toward the end of the z-axis, that will be waves travels to along the z-axis. Okay, due to this delta that having the difference in that angle of that EX and EY, that will be you are getting the elliptically polarized light. And at the end of this means you are the suppose you have to check this wave at, therefore this is a plane EX is perpendicular to EY, means EY and EX that is having 90-degree perpendicular to each other, and this we are showing that therefore this is the electrical field, and this the EO0x, the electrical axis at corresponding this point, and this UOY. Okay, and we are the having that we are rotating this means that is we are getting the elliptical form here at the end of this. Suppose this waveform we are checking here, then end view that we are getting this one, and this is a alpha angle that in between of EX and EOX. This is a EX. Okay, and that is a elliptical this point. This is elliptical points that we are getting that at x axis, EX axis, and EY axis EOY. Okay, and this plane we are forming here, and we are rotating that signal, means that due to the delay of that angle delta, due to that this elliptically that points we are getting, this will follow the elliptical form. Okay, this is the elliptically polarized light we are showing. If there is a in between of EX and EY plane, we have the delta as the angle difference between two planes, not started the two yeah, fields at a particular same point, that having the difference of delta, that will we are showing here. Okay, that we therefore that is a, we are getting the elliptically polarized light here, elliptical form at the end of that. If you check here at the z-axis, that center of the, this is a particular z points, that is a perpendicular to EX and EY, that is a 90-degree mutually perpendicular to each other three axes. And end views, they are, this is we are getting EY, so we are calculating that in terms of EOX and EOY. We are not showing here the magnetic field, we are talking about the electrical field for the EX and EY two fields that we are showing here. Okay, and next is that this is a circularly polarized waves. Okay, here how that is circularly polarized, that waves we are showing here, direction of wave propagation along the z-axis, already we are talking about that. And here again, that is a, we have the circular polarized waves, that we have the EX and EY that having the 90-degree, therefore that comes here circular polarized EX and EY. Okay, here in previous that only delta factor is there, here we have the difference here, del EX and EY, this is a EY and this is a EX. Okay, that these are two fields, we are perpendicular to each other, and that time that having the 90-degree perpendicular means 90-degree difference is there, therefore at it is a peak point of this EX, that we are getting a null of that EY. Okay, this EY axis, EY electric field, and this is EX electrical field. Therefore, that we are getting this just like a circular, not elliptical. This is the elliptical means less than 90-degree, that having the difference between EX and EY plane electrical field. But here in circularly polarized waves, we have the 90-degree phase shift, and therefore we are getting at the end of this, taking about the end view of this. Suppose we are checking that, then we are getting the circular type end view. Okay, and that we are getting EX and EY, and resultant is E. That will we are getting the circularly polarized wave, so in the circular form. Okay, here well, actually okay. Uh, then the first three parameters are scalar characteristics of light, where the light parameter polarization describe the vector nature of light. We are talking about the light, that is how the vector nature of light, and the parameters are scalar characteristics of light, whereas the last parameter is polarization, describe the vector nature of light. The polarization is the intrinsic property of an electromagnetic wave. What is polarization? That is the intrinsic property of an electromagnetic EM wave. That is the polarization of the wave. Polarization is the intrinsic property of an electromagnetic wave. The choice of wavelength depends upon the loss profile of the medium. The choice of wavelength depends upon the loss profile of the medium. For optical fiber, the wavelength has to be 1300 nanometer or 1500 nanometer for low loss. Here the 1310 nanometer actually, that is a 1310. This one is 1310 nanometer, or the or 1550 nanometer for low loss. This is for second window and third window. The choice of wavelength depends upon the loss profile of the medium. For optical fiber, the wavelength has to be 1310 nanometer or 1550 nanometer. Okay. Akash, you have to join at a starting of the lecture. Okay. Akash. We should be joined before the start of the lecture. The spectral width has direct bearing on the data rate which the medium can support. Larger the spectral width, smaller is the data rate. Okay, if you have the larger the spectral width available, then smaller is the data rate. Here the when we are talking about the LED, that is having the more spectral width available. Okay, that is a 36 nanometer, the spectral width of the particular LED spectrum. That time we have the low data rate transmission. But when you are considering that is a laser, the laser as a source, that time that having the spectral width of 9 nanometer ideally. Therefore, that is a narrow one beam is available. Therefore, the more focused one beam you are getting, therefore that will be used for the long distance transmission, and that having the high data rate transmission that can be used. Therefore, that is a laser source as used for the single mode fiber for long distance transmission. That is only one mode that will be transfer, or that will be pass the signal, or that will be transmitted the signal from source to the detector through the cable, through the core. That is a channel. That is the use of that spectral width has direct bearing on the data rate, which the medium can support. That medium is the channel. We are using the optical channel. Larger the spectral width, smaller is the data rate. Smaller the spectral width, then larger is the data rate. That is inversely proportional to each other. Okay. Therefore, the for long distance transmission, when we are using the single mode fiber, that time definitely you should require as a source as a laser source, and therefore the beam of that having focus one, and that will be used for to long distance transmission signal from transmitter to receiver. Okay, for a long haul transmission system. Then here the spherical and plane wave fronts, wave fronts. Here we are showing the spherical one. This is plane wave fronts. Okay, for a single point source. Let's suppose LED or laser. We are using the suppose LED, the spectral wave fronts. This is spherically that will be pass the rays. That we are showing. We are getting here, but at a particular point on the rays and that plane, that we have the spherical wavefronts. That particular point that having the 90-degree, that will be maintained on that each point. Here also this 90-degree. Here this particular point, this one, and this one. Here the plane wave fronts, the rays pass, that will be having plane wave fronts vertical, and that 90-degree to rays form. Okay, the light is an electromagnetic wave. That having the light is an electromagnetic wave. It consists of wave fronts. The lines normal to the wave fronts are called the light rays. It consists of a wave fronts. This is the wave fronts are there. Okay, we are passing from a single source of point here. The more than not a single point here, the separate rays are available. Means suppose there is three sources, then three rays that will be passed. For example, we are considering it consists of wave fronts. The lines normal to the wave fronts. These are the wave fronts, plane wave fronts, vertical. This is a spherical wave fronts, because we are starting the emission of the light from the single source of light, the single point source. Okay, and these are the rays are parallel to each other, and therefore that is a perpendicular to the plane wave fronts. Okay, therefore that it consists of wave fronts. The lines normal to the wave fronts are called the light rays. If the phase fronts are concentric spheres, the light is called a spherical wave, and if the phase fronts are parallel planes, the light is called as a plane wave. Okay, that we have defined here. If the phase fronts are concentric spheres, we are getting spherical form. Okay, the spherical, the light is called as a spherical wave. Therefore, the light is called as spherical wave fronts. And if the phase fronts are parallel planes, these are the parallel planes, vertically, and the light is called as a plane wave. Therefore, this light is rays fast, that is called as a plane wave. Then the important rules to remember: in vacuum, rays travel at velocity 3 into 10 to the power 8 meter per second. In a vacuum, rays are travel with the velocity of light. C is equal to 3 into 10 to the power 8 meter per second. And in another media, the speed is lower and is given by the refractive index and effective refractive index. Okay, the and other media, the speed is lower and is given by refractive index n. The refractive index is calculated, small n is equal to c by lambda, the velocity of light in vacuum to the velocity of light in medium. Therefore, that indicated the refractive index is equal to n small n is equal to c by v, velocity of light in vacuum and the velocity of light in medium. Therefore, we are getting the refractive index n. Okay, already we are talking about the velocity of light is and just we have mentioned here also 3 into 10 to the power 8 meter per second. And if you know the velocity of light in medium, then we are getting the refractive index n. Okay, that we are calculate c by v. The effective refractive index, that is a n effective for a bound medium, is again the n effective is getting c by lambda, same formula for the refractive index n and effective refractive index n effective. So therefore that also c by lambda. If you know the n effective and c, then we already know the c, then we getting the v, that is the velocity of light in medium. If you know the v and already you know the c, then we'll get the effective refractive index value. Okay, here this is an important one, the index of refraction for some materials. Okay, that is here we have the refractive index n, that is we have calculated velocity of light divided by the we have the divided by v, we have mentioned the v, that is the velocity of light in medium. That is, suppose light pass through the core, then that velocity of light of that core and the velocity of light in vacuum, that is a c by lambda, we are getting the refractive index of that. Effective refractive index also for a bound medium, that is also same, with the help of c by lambda we can calculate. Then the here we have the 1. Therefore, c by means refractive index n is equal to c by lambda. Therefore, n is 1, c is 3 into 10 to the power 8 meter per second. Then we will be getting the lambda value. Okay, that is we are getting the lambda is equal to 1 upon 3 into 10 to the power 8. That is a lambda is equal to 1. That is a 0.003 into 10 to the power minus 6 or meter, minus 6 meter. We can get the values. Then water, we have the water having the refractive index 1.33, magnesium chloride that having the refractive index 1.38, fused silica SiO2 that point having the 1.46, and we have Al2O3 that is a sphere that having the refractive index is 1.8, lithium neobate, neobate is that is LiNbO3, that is having the refractive index is 2.25. Then indium phosphide INP, that is a 3.21, gallium arsenide GaS 3.35, silica 3.48, only silica, silicon, not silica, silicon, and fused silica SiO2 that is 1.46. But silicon Si that is a 3.48, indium gallium arsenide phosphide INGaAsP that is a 3.51, and aluminum gallium arsenide AlGaAs that is a 3.6, and germanium we have the 4. Okay. The index varies with a number of parameters such as wavelength and temperature. On the basis of that, we have the varies the index value of the refractive index. Okay, these are the important. Okay, that will be another diamond also there. Okay, that having the diamond values 2, but that is a costlier, generally not used the diamond. Here an optical fiber basically is a solid glass rod surrounded by concentric glass shell is as shown in figure. Already we have discussed in the first unit also. We have shown the video also for that, how that is a construction of the fiber, how that fiber looks like. Here the core, above the, that is with the help of the glass we have to make the core or plastic also. Okay, then here the above that the cladding, and then that cladding also with the we can make with the help of the SiO2 or plastic also. Okay, and above that the buffer coating to protect the fiber. Okay, to protect the core and cladding. We have to do it because the core and cladding is make with the help of the silica SiO2. Then that having the more less strength in that glass, and therefore the buffer coating is important for to give the strengthness to the fiber. Then here the lambda, the for the light to propagate inside the fiber through the total internal reflection at a core cladding interface. The refractive index of the core must be greater than the refractive index of the cladding. Therefore, already we have discussed previously also, N1 is greater than N2. Suppose N1 is, suppose we are using silica SiO2, then that having 1.48, then cladding should be, you have to add some impurities in that glass. Therefore, that refractive index will be less than that of N1. That will be 1.47 or 1.46. That depends upon the how much concentration of that impurity we are adding to that glass, and therefore that refractive index is reduced. If you are with the fluoride, then another material also. Already we have discussed about the where the material of lithium carbonate, then indium phosphide, then that will be the change the refractive index of that core. Okay. For the light to propagate inside the fiber through total internal reflection at core cladding interface, that is we have to so check the suppose we'll discuss next figure that how the we are getting the internal reflection at core cladding interface. The refractive index of the core must be greater than the refractive index of the cladding. Here this is the plane diagram for the we are getting the refraction of the light. Here this is follows the Snell's law here. Okay. Here this is N1 and N2. So therefore N2 is less than N1. Means N1 having the medium that having the refractive index is greater than that of N2. Okay. That is the meaning. N1 is greater than N2 or N2 is less than N1. Okay. Definitely this we have to require N1 is greater than N2. And here the denser to rear. This is a rear. Suppose this particular plane is rear, and this is a denser to rear. More denser, the denser to rear material. This particular plane. This is called plane. This is a particular. This is a suppose material boundary, and that this is a normal line. They are available. So this is a material boundary that having the medium N1. And denser to rear, this is a medium 1 mean that is a rear plane. Then this is a rear medium. This is a denser to rear, that is we have the medium 2. Okay. And if you want to add the impurity, then N2 is less than N1. And here N1 is greater than N2. Therefore, this is a material boundary and this is a normal line to this plane. Okay. That will you have to follow the Snell's law also. This is an incident ray. How that incident rate we are showing phi1 and this is a phi2. Okay, this is a incident ray. Suppose critical, we are also thinking about the critical angle also. When that critical angle theta c, phi c is that 45 degree, then that light is passed along this material boundary. When phi c is less than this the phi theta 1 or this is a phi c is less than 45 degrees. Okay, I'm sorry, phi 1 is greater than phi 1 is less than phi c, that is a critical angle. Then that will be suppose here at 45 degree that phi c is available here. This range I am talking about the how the incident range, that is where the source is there and you are incident on that particular plane point at the material boundary, and you have to set the angle also. Okay, and this is normal to the plane at this particular point, and after that you have the getting the rate. This is a suppose the theta c is less than fc is less than suppose f1, means you are having that less than that critical angle, then the total reflection that comes here, no refracted rays. Therefore, single the reflected rays, that is a total, that is called as a total internal reflection. This is a particular plane. This is having suppose a core, and this is a denser medium that is having the cladding. Therefore, these two planes are available. One plane is the core, and that is a having the rear region, and after that that is a denser to rear. Means you are adding some impurity, denser medium is available, and we have that is a form for this particular plane used for the cladding, and we have incident the line to that plane that will be there here the at a particular point. Therefore, that we are getting the suppose that phi 1, that is we are talking about the critical angle. Okay, this suppose critical angle is 45 degree. Then this rays pass through the material boundary. This along this. That is we are getting pass through this a 90 degree. That will be form the theta 1 as a 90 degree. Okay, that is an if your phi 1 is less than critical angle, then you total internal reflection, no refracted rays are available there. Total internal reflection. Already you are studying in the physics also that concept. Okay, that is you have to check the with the Snell's law. Therefore, n1 sine phi 1. If you are here, suppose draw the line here and you have this 90 degree, find out then. Therefore, n1 sine phi 1 is equal to n2 sine phi 2. Therefore, n1 upon n2 is equal to sine phi 2 upon sine phi 1. Okay, that will be calculated, and you are getting the Snell's law. Okay, the n1 sine phi 1 is equal to n2 sine phi 2. If you have connected this point and we are getting a 90 degree and we have find out the sine phi 1 and sine phi 2. Therefore, n1 upon n2 is equal to that we are getting n1 sine phi 1, n1 upon n2 is equal to n1 into upon n2 is equal to sine phi 2, and that is here we are getting sine inverse phi 1. Okay, that will be our writing, that is n1 sine phi 1 is equal to n2 sine phi 2. Okay, then here these are the critical we are showing that the when phi 1 is less than phi c, this incident light is phi 1 is less than phi c. This is a phi c, suppose we are phi 1 is less than phi c, means suppose phi c is 45, then that phi 1 should be less than of phi c, that should be 40 degrees. Suppose that time the rays so when that is a phi 1 is less than phi c, then that we are getting the refracted and reflected rays. When phi 1 is equal to phi c, means that is a 45 degrees, suppose phi c, and there we are getting phi 1 is 45, then that rays is along the plane, that is a where you are joining of two planes, material boundary, that will be fast. Okay, and this is not available there. Okay, this is not available, but that is follows along the uh, x-axis. Therefore, that the normal to the plane and x-axis that having the 90 degree. Okay, that will be maintained. Therefore, phi 2 is 90 degree. This is normal plane and x-axis. When phi 1 is greater than phi c, more than 45 degrees, suppose phi c is 45, then phi 1 is suppose 50 or 60. More than that time that is a total internal reflection that will be taking place here. Here, total internal reflection. Means there is no rays, refracted rays, no refracted rays available. That when phi 1 is greater than phi c, that is total internal reflection will be take place, and you can find out the theta 1 also. Okay, if phi 2 is 90 degrees, so that sine phi 2 is equal to 1. Therefore, sine phi c is equal to n2 upon n1. You have to put this value in this equation. N1 sine phi 1 is equal to n2 sine phi 2. You have to put the values there. Phi 2 is 90 degree. Here phi 2 is 90 degree, and therefore we can calculate the sine phi c is equal to n2 upon n1. N2 is the refractive index of the cladding, and this n1 is refractive index of the core. This is a meridional ray. This is a particular, this is a fiber actually. This is a core and cladding. Okay. Here you have shown the structure of the cladding. Just end view, not end view. There is a, you have cut the fiber, and that you are getting the rectangular form. That's fiber here, and we are showing this particular how the rays we are parted. Suppose that we are the critical angle that will be there, and then that will reflected rays comes, and that rays pass from core to the cladding, and again that comes back. This is also glass, but that adding of impurity. That n2 is less than n1. There again that the reflecting is less than that of n1. Therefore, definitely that from the boundary of this cladding that reflected back to the core that rays. Okay. When that theta 1 phi 1 is equal to phi c, that rays passed along this z axis. This is a z axis. Okay, that is means that rays along the z-axis. Okay, and therefore this theta is 90 degree that time from this plane normal to the plane this one, and x-axis that is a 90 degree. When you have the theta 1 is greater than 5c, that time you are getting the internal reflection just of this diagram. Phi 1 is greater than 5c, then internal reflection, total internal reflection in the plane, in the core region, that will be there. Therefore, that is shown phi 1 normal to this plane and this phi 1. Phi. Therefore, we are getting the total internal reflection that we have to adjust the angle of this incident angle. This is a single incident angle from the source where incident light will show, point out this particular point. We are getting that. Okay, internal reflection, refraction. Okay. This three waveform that comes here, but here this is not available. Huh? This particular part is not available here. This arrow, this line, this is not there. Only when that is a phi 1 is equal to phi c, that time that this phi 2 is 90 degree. Okay, this plane, along the plane, this material bonding, that rays is passed. Therefore, this we are showing the how this Snell's law and how that refractive index of the core and cladding we are showing. Okay. Then skew ray. Yeah, now lecture is over. Time is over. Hello.
Yes, sir. Yes, sir.
Time is okay.
Yes, sir.
Okay. Okay. You have to write down your name in the chat box. Everyone. Do not join late to the lecture. Right time you have to join. Continuously I have to add those students. That is difficult to me switching from PPT to that. It's over. Completed.